We are now into section 4, the matching column type section. Let's look at question 16 from this section. It says 5 conducting large plates, each of plate area A, are arranged parallel to each other and they are given some charges as shown. Now plate C is earthed. Considering the effect of earthing of plate C and conditions after that, match the entries of column 1 with those of column 2. So the 5 plates are given here and the charges on each plate is given. And in column 1, the entries are potential difference across A and B, potential difference across B and C, potential difference across C and D, potential difference across D and E. In column 2, entries are increases, decreases, QD by epsilon naught A, 3QD by epsilon naught A, 0. So to solve this question, we show the charge distribution on the plates before C is earthed and then again after C is earthed. So before plate C is earthed, let's draw this 5 plates. So we have these 5 plates now. Now we know on the outermost surfaces of the first plate and the last plate, the charge Q can be given as, if I say the charge here is Q1, here also it's going to be Q1, and this value of Q1 is going to be equal to sum of all the charges, summation Qi divided by 2. In our case, this value is Q plus 2Q minus Q plus 3Q minus 3Q divided by 2. We see that its value is these two exactly cancel, and then we have these two exactly cancel. It's 2Q by 2. That means its value is simply Q. So with that, we can show the charge distribution easily. Here it is then Q. Here it will be 0. This of course is before earthing of plate C. And since, okay, so here also it will be 0 and then here it is 2Q. Then here it's going to be minus 2Q. Since plate C has charge minus Q, so on this side there will be plus Q. And again here it's going to be minus Q. Here it's going to be then plus 4Q. And here also again it's minus 4Q. We can see that here again it's Q. This is the charge distribution on the surfaces of the 5 plates. This is before earthing of plate C. What happens when plate C is earthed? So we can write here, this is before. And what happens after? So once plate C is earthed, on the 2 outermost surfaces of the left plate and the right plate, the charge will become 0. So the new charge distribution will look like this. C is being earthed. So on these 2 surfaces we have 0 charge. Now here it is Q. Obviously it is minus Q then here. And then it becomes 3Q. Then here is minus 3Q. On this side is 0 charge, so there is minus 3Q here. And so plus 3Q will come here. So there is 0 charge here and 0 charge here. Let's look at the options now. Potential difference across A and B initially was 0. The final potential difference across A and B can be given as Q by C. The charge now on the surfaces facing each other is Q and minus Q. So it's Q by epsilon naught A by D. So for A, potential difference across A and B increases because initially it was simply 0 and now it is this. So A corresponds to P, and in terms of value it matches with R, so A matches with P and R. Let's look at B now. For B, potential difference across B and C. Initially, it was the potential difference corresponding to charge 2Q, and finally, it is corresponding to charge 3Q after earthing. So potential difference increases. So that means for B, we have again P. The new value of potential difference will become 3Q by epsilon naught A by D. So that means it matches also with S. Let's look at option C now. I mean the entry C of column 1. Potential difference across C and D, this was D plate here. It was corresponding to charge Q and minus Q on these two plates. And finally, here charge is 0. So that means the potential difference has decreased and has become 0. So C corresponds to Q and potential difference has become 0. That means it also matches with T. Let's look at D now. So earlier the charges were 4Q and minus Q, 4Q, and finally it is 3Q and minus 3Q. That means potential difference has decreased and it again will be equal to 3QD by epsilon naught A. So that means D will match with Q and S. So this is our matching for question 16. Let's go to the next question now. Question 17 says, column 1 contains 4 thermodynamic processes of an ideal diatomic gas, and column 2 contains properties of those processes. Match the entries of column 1 with those of column 2. So in column 1, we have graphs for various thermodynamic processes. And in column 2, we have entries like internal energy increases, internal energy decreases, heat is absorbed by gas, heat is released by gas, and internal energy remains unchanged. Let's start with entry A. So in A, there's a PV graph where P is proportional to 1 by V. That means PV is equal to constant, or which means that the process is isothermal process in which volume is increasing. So it's isothermal expansion. Now in isothermal expansion, obviously internal energy remains constant and work done is positive. That means delta Q is also positive, which means for A, the options that will match is internal energy remains unchanged and heat is absorbed by gas. That means A matches with R and T. Let's look at B now. B, we have graph of density versus pressure. We can see that it's a straight line. When extrapolated, it passes through the origin. So for the process B, density is directly proportional to pressure. So we can write rho is equal to some constant K into pressure, and rho can be written as mass by volume is equal to K into P. So we have PV is equal to constant. So that means process B is also an isothermal process, but here pressure and density are increasing, which means volume is decreasing. So B is a case of isothermal compression. If that is the case, then internal energy will remain unchanged, but the work done by the gas will be negative, which means heat will be released by the gas. So for B, then we have S, heat is released by gas, and T, internal energy remains unchanged. Let's look at C now. For C, we are given T into rho is a constant. T is proportional to 1 by rho. That means T into rho is a constant. Or T into mass by volume is constant, which means T into mass is proportional to volume, which means it's a isobaric process. So C is isobaric process in which density is increasing. So it's a case of isobaric compression, and in isobaric compression both delta U is negative and the work done is also negative. So if we look at entries in column 2, we can see that for C internal energy decreases and Q heat is released by gas. So for C, Q and S will match. Let's now look at entry D. For D, we can see that the product of pressure and volume initially is 3 P0 V0, and we can equate it to NR, let's say initial temperature. Let's call this point A and this point as B. So at A, the product of pressure and volume is 3 P0 V0, and at B, the product of pressure and volume is 3 P0 by 2 into 3 V0 by 2. That means it is 9 P0 V0 by 4, and that is equal to nRTF. So it's very clear that Ti is greater than Tf, which means U decreases, internal energy decreases, but work done is positive. So to evaluate whether heat is rejected or released by the gas, we need to calculate both change in internal energy and the work done by the gas. So let's first write work done by the gas. Work done by the gas is equal to area of the trapezium, and that is equal to 1 by 2 into height. Height is V0 by 2 into sum of parallel sides, which is 3 P0 plus 3 P0 by 2. This will simplify to 9 P0 V0 by 8. Let's also look at delta U. Delta U is equal to N. It's a diatomic gas, so Cv is 5R by 2. So N into 5R by 2. Tb minus Ta or Tf minus Ti, and this is equal to 5 by 2. nRTB or nRTF we have seen is 9 P0 V0 by 4, and then nRTI or nRTA will equal 3 P0 V0, which means delta U is equal to minus 15 P0 V0 by 8. So if we add up W and delta U, quantity is still negative. So that means delta Q is also negative for the process D, which means for D, the entries that will match are internal energy decreases and heat is released by the gas. So Q and S match for entry D. So this is our answer.